everyone, welcome back to Tales of Chemistry. Today we are discussing part 3 of chemical kinetics. In this, mainly we are going to learn the meaning of elementary and complex reactions, integrated rate expression for first order reaction, half-life of a reaction, and numericals based on integrated rate law as well as half-life period. Now, what is an elementary reaction? Reactions that take place in one step, that is, single step reactions, are called elementary reactions. Now, in such reactions, that is elementary reactions, order of the reaction is equal to molecularity of the reaction. Now, what do we mean by molecularity? We mean the order is also equal to the total number of moles that take part in the reaction. Look at this. Though I have written H2 plus I2, we mean 1 mole of H2 combines with 1 mole of I2. Okay, so here the order of the reaction is 1 plus 1, which is equal to 2, which means rate can also be written as K into H2 to the power of 1 into I2 to the power of 1. And this will happen only in the case of an elementary reaction. There is a possible question to explain what elementary reactions are. Then, complex reactions. Reactions which take place in more than one step. 2 or more steps are called complex reactions. Reactions that take place in more than one step are examples for complex reactions. Each step in a complex reaction is an elementary reaction, and the slowest step will be the rate determining step. Okay, now complex reactions cannot be identified. This is for you if you're thinking, can we just look at the balanced equation and find out whether a particular reaction is elementary or complex? No, you cannot. Okay, so the difference between elementary and complex reaction is very important to keep in mind. It can be a 1-mark question to differentiate between elementary and complex reactions. Now, what is this integrated rate expression for a first order reaction? Zero order reaction is not in ISC syllabus. That's why straight away we are doing this first order reaction. Now, to represent a first order reaction, I have taken A gives products. Now, rate of the reaction. I can write the rate of this reaction in 2 different ways. One, R is equal to K into concentration of A. That is because I know this is a first order reaction. I can also write R is equal to minus d by dt of change in concentration of A. This is how we started learning rate, isn't it? Minus sign because it is reactant, d by dt, a small change in concentration of A with respect to a small interval of time. Okay, now, but both represent the rate of the reaction, which means minus d by dt of A is equal to K into A. Now, let me take like terms to one side, that is dA, okay, by A. That is equal to K dt. Now, this is for a tiny interval of time. This dt is a very small interval of time, and dA is a negligible change in concentration. But I need the rate for the entire reaction. So we are integrating. So minus integral 1 by A with respect to dA. Integrate, okay, 1 by A with respect to dA, that is equal to K integral dt. Now, 1 by A dA is ln log A. So ln stands for natural log. And on the other side, K integral dt is T. Plus I'm writing a constant of integration C. Now if you're thinking why the constant of integration is only on one side. Well, it's there on both sides. Now, since it is a constant, I have collected it from the left side and written only on the right side. Okay, so now I need to find an expression for C. So to find C, let T is equal to 0. What do I exactly mean by T is equal to 0? Beginning of the reaction. T is equal to 0 means we are just starting the reaction. And instead of A, I can write A naught, where A naught is the initial concentration. So substitute this in the first equation. Let me call this equation number 1. Okay, so when I substitute this, minus natural log A naught is equal to K into 0 plus C. So I get an expression for C. C is equal to minus ln A naught. Substitute the value of C. Substitute C in equation 1. Okay, so you get minus ln A is equal to KT minus ln A naught. Now, take this minus ln A naught to the right side. Ln A naught minus ln A is equal to KT. Okay, so KT is log x minus log y, is log x by y. So this is ln A naught by A, concentration of A naught by concentration of A. This is natural log. I need it in, log to the base 10. So KT is equal to 2.303. To convert ln to log, ln stands for natural log, log log to the base 10. So multiply it with 2.303 log initial concentration by concentration at time t, what remains at time t, not what is over. So K is 2.303 by T log A naught by A. Once again, A naught is the initial concentration. A is what concentration remains at time T. So this is the expression for K, or this is what we call the integrated rate expression. Integrated rate expression for a first order reaction. Learn the derivation even when it was never asked to derive, but it is very much there in syllabus. So please learn the derivation also. Now, graphical representation for a first order reaction. Rate is plotted against concentration of the reactant. So you get a straight line like this. So learn to draw the graph as well. Okay, now one more is, suppose if you are drawing, let me do it here, or you're plotting log A against T, log A against T, okay, then you get a graph like this. You get a graph like this. This is for log A, that is concentration that remains at time t against t. But this intersection, this point will be representing log A naught. Also, the slope of this line, slope is minus k by 2.303. Slope is minus k by 2.303. Now, instead of this, suppose you're plotting log A naught by A against t, then your straight line is of this order. And here, slope, okay, is k by 2.303. So if the question is rate against concentration of reactant, this is how we represent a first order reaction. Log A against T, this is the graph. Log A naught by A against T, this is how the graph is to be plotted. And in these two cases, the slope is also given. Please make it a point to learn the graphical representations. Now, half-life of a first order reaction. What is the meaning of half-life? Time required for 50% of the reactants to get over. Time required for 50% of the reactants to get over. That is what we mean by half-life of a reaction. So first I have written here the integrated rate expression. Now I'll take T to the right side because now I am explaining half-life, which is the time required for 50% of the reaction to get over. So T is 2.303 by K log A naught by A. Now, just because we are discussing half-life, I am writing this T as T half. So we will get a clear idea that we are discussing about half-life, which is equal to 2.303 by K log A naught by A. What is A? 50% of the reaction is over, which means A is nothing but A naught by 2. A is nothing but A naught by 2. So when I cancel the two A naughts, what I get is 2.303 by K log 2. Now, T half is therefore 2.303 log 2 is 0.3010 by K. So on multiplying this, we will get T half is 0.693 by K. Yeah, T half or half-life of a reaction is 0.693 by K only for a first order reaction. So learn the derivation, learn the final formula also. Moving on to numericals, the first one, show that for a first order reaction, the time required to complete 75% of the reaction is twice the time required to complete 50% of the reaction. Time required for 75% of the reaction. Okay, so we are actually getting a ratio between T75 and T50. T50 is nothing but half-life of the reaction. So you can straight away write T50 is 0.693 by K. Or else you can just keep it as 2.303 by K. Okay, log 100 by 50. Which on solving you will get 0.693 by K. T75 will be 2.303 by K log 100. Okay. 100 is the initial concentration. 75 is over. 75 is over, which means 25 remains. So this becomes 2.303 by K log 4. So first of all, we need the value of log 4. Okay, log 4 should be around 0.60 something. Anyway, let me check. Log 4 is 0.6020 by K. All right. So we are not solving this at this stage. And also here, you know, okay, here you know, T50 is 2.303 by K log 100 by 50, which is 2.303 into 3010 by K. Now, T75 by T50, just 3 steps are needed to solve this. T75 by T50 is 2.303, 0.6020 by K, and T50 is 2.303, 0.3010 by K. So that K I'm writing here. So cancel out all the common terms. You will get 6020 by 3010, which is equal to 2, which means T75 is equal to 2 into T50. Time required to complete 75% of the reaction is twice the time required to complete 50% of the reaction. Okay, so that was the first question. This is 2019's board question. Now, moving on to the next. A first order reaction takes 100 minutes for completion of 60% of the reaction. So when T is equal to 100, 60% of the reaction is over. Find the time required for 90% of the reaction. So T90 is what you should calculate. Okay, so first of all, to calculate T90, I need the value of K. 2.303 by K log 100 by 10. 90 is over. 90% is over. So there remains only 10%. So 2.303 by K log 100 by 10. All right. But I don't know K. To find out the K, the first data is given. That is K is equal to 2.303 by 100 time log 100 by 60 is over, so 40 remains. 10 by 4. 10 by 4 is 2.5. So this is 2.303 by 100 log 2.5. So initially check what is log 2.5. Okay, log 2.5 is 0.3979. This by 100. So multiply 2.303 with 0.3979 divided by 100. You are getting some 0. Just give me a second. 96 or so. 916. 0.00916 per minute. Okay. Fine. So here, since the data given is minutes, so we could easily identify that this is per minute. So K is calculated. Once K is calculated, use that value of K in the T90 formula. 2.303 by K log 100 by 10. So it is 2.303 by 0.00916 log 10. Log 10 is equal to 1. So this becomes 2.303 by 0.00916, which is around 251.42 minutes. 251.42 minute. You can leave that answer in minute. You don't have to convert it into second or hour. Whatever unit is given in the question, retain the final answer in the same unit. That is it. This was also a board question, 2022's board question. This was. One more question. In a first order reaction, 20% of the reactant is consumed in 30 minutes. 20% is consumed in 30 minutes. So T is 30 and 20% of the reaction is over, 80% remains. Calculate half-life. To calculate half-life, formula is 0.693 by K. But I don't know K. So I'll use this data to check K. K is 2.303 by 30 log 100 by 80, log 10 by 8. So first of all, find out log 10 by 8, then substitute. You can solve it yourself. Now, the answer is 0.00744 per minute. Substitute that here, 0.693 by 0.00744, which gives you 93.145 minute. That is half-life of the reaction. Second part of the question is time required for 93.75 completion. All right. So T 93.75 will be 2.303 by K log 100 by 93.75 is over. So 100 minus 93.75 will remain. That will be 6.25. So here the denominator is 6.25. So first of all, solve 100 by 6.25. find out the log of that number and substitute k also, 2.303 by k, 0.00744, and log 100 by 6.25. Okay, so 100 by 6.25 is 16. Log 16 is to be calculated. So on solving, this will be 372.73 minute. Okay. Final answer 372.73 minute. Okay, so solve more questions from your reference material and please stay tuned for more videos. Thank you.